Okay, we are starting section 4.4, which is going over the fundamental theorem of calculus. So when we have a continuous function on a closed interval from a to b, and you have capital F as the antiderivative of little f on an interval, then what we do to find a definite integral, so definite integral means where you have a and b instead of no limits at all, you take the integral of the function and then you plug in the top number, b, and subtract off plugging in the bottom number, a. We can also write this as capital F evaluated from A to B. That's just another way to write it. But essentially what you're doing is up above here, plugging in B followed by plugging in A and subtracting the two values. Okay, so what we're going to do is take the integral of the function, which is x cubed over 3 minus 3x. We are evaluating that from 1 to 2. So we plug 2 in. Oops. Plug 2 in for x. And then subtract off, plugging 1 in for x. And when you evaluate that correctly, you get negative 2/3. Okay, b, 3 times the square root of x, we would need to rewrite that as 3 times x to the 1/2 dx. And then we take the integral, 3 times x to the 3/2 over 3/2, evaluated from 1 to 4. Which is 2 times 4 to the 3/2 minus 2 times 1 to the 3/2, which is 14. Part C is the integral from 0 to 4 of secant squared. The integral of secant squared is tangent, and we're evaluating that from 0 to pi over 4. So tangent of pi over 4 minus tangent of 0, and that is 1. Okay, this time we have an integral that has an absolute value. So we need to figure out, because absolute values, if we can think about what they look like, are always v's. So this, if we split up into two different functions, one of them is negative 2x minus 1, and that's when x is less than 1/2. And we also just have regular 2x minus 1 when x is greater than or equal to 1/2. And the graph of this function at 1/2 is where they split off. Oops, that's not very good. A little more accurate. Starting at 1/2. There we go. And at 2, it should be at 3. So just be careful there. There we go. And we are looking at the area from 0 to 2, which will make us these two triangles. Okay, so you have to take the integral of actually two separate ones. We need to add up the integrals of both of them. So starting with the integral of 0 to 1/2 of negative 2x minus 1 dx, we have to add on the integral of 1/2 to 2 for 2x minus 1 dx. Okay, so the integral for the first one is negative x squared plus x evaluated from 0 to 1/2. And we're adding on x squared minus x from 1/2 to 2. And if you plug in 1/2 into the first one, followed by 0, plug in 2 and 1/2, your final answer will get 5/2 or 2.5. Find the area of the region bounded by the graph 2x squared minus 3x plus 2, the x-axis, and the vertical lines 0 and 2. The only thing that means when you have 0 and 2 is that means those are your limits. So let's do a rough sketch of this here. We only care about 0 to 2. Alright, that's roughly what it looks like. The important thing is to do the math correctly. Okay, so it's going to be 2/3 x cubed minus 3/2 x squared plus 2x evaluated from 0 to 2. And when every term has an x in it, like it normally will, if it's a polynomial, you actually don't even have to plug in the second half, the 0, because it's going to give you 0. So let's just plug in 2 into every term, and we get 3 1/3. Okay, mean value theorem. If f is continuous on a closed interval from a to b, then there's some value in between a and b that if you multiply by b minus a, f of b minus a, you will get the average value. So the more important theorem is actually on the top of the next page. The rule to finding an average value on an integral is 1 over b minus a times the integral of a to b fx dx. So it's the same thing, take the integral of fx dx, but the difference is we have to multiply by 1 over b minus a, which is the average value of the interval. Okay, so let's go ahead and find the average value of this one. We're going from 1 to 4. Taking the integral of our function, we have to remember out front to do 1 over 4 minus 1. Okay, so it's going to be 1/3 times the integral. So x cubed minus x squared, and that's going to be evaluated from 1 to 4, which is 1/3 times 48 once you evaluate the integral, which is 16. So it's really important not to forget to multiply by the average value out front. That'd be a silly thing to get wrong if you've done everything else correctly thus far. Okay, here we have different altitudes in Earth's atmosphere. Sound travels at different speeds. The speed of sound is modeled by this function. So there's several different intervals here. We have 5 intervals. With x as the altitude in kilometers, the question here is what is the average speed? Over the interval from 0 to 80. Okay, so we actually have to find the average value. So because there's 5 different intervals, we actually have to find the integral of each one of those and then add them together. So our first one is going to be from 0 to 11.5 of negative 4x plus 341 dx. The integral of that is negative 2x squared plus 341x evaluated from 0 to 11.5, which is 3,657. Okay, I'm going to go fairly quickly here just to make sure that we can get through everything on one video. Next one is 11.5 to 22. Our function is 295. Integral of 295 is 295x. Evaluate that from 11.5 to 22, and it's 3,097.5. Next one is from 22 to 32, and the integral of 3/4 x plus 278.5 dx. Integral is 3/8 x squared plus 278.5x. Evaluate that from 22 to 32, and you'll get 2,987.5. Next one is from 32 to 50. 3/2 x plus 254.5 dx. Take the integral, and it's 3/4 x squared plus 254.5x, evaluated from 32 to 50, 5688. Then we have the last one, then we need to add them all up. Last one is from 50 to 80. Negative 3/2 x plus 404.5 dx equals negative 3/4 x squared plus 404.5x from 50 to 80, which is 9210. So once we add all these up, the summations of all of our integrals from 0 to 80 is 24,640. So to find the average speed over the interval from 0 to 80, we have to multiply our summation. So that's 24,640. Divide that by 80, which is 308 meters per second. All right, the next one. If we're evaluating a function from 0 to x of cosine t, we take the integral of that, cosine t dt. The integral is sine t, and we're evaluating it from 0 to x. So we plug in the top one, subtract off the bottom one, and we just get sine of x. And so we have to plug in each one of those values. F of 0 is 0. F of pi over 6 is 1/2. F of pi over 4 is a square root of 2 over 2. F of pi over 3 is a square root of 3 over 2. And f of pi over 2 is 1. That's all we needed to do. We needed to evaluate the integral, which was sine of x, and then plug in each one of those functions, values. Okay, so the second fundamental theorem is if we have a continuous function on an open interval that contains a, then for every x in the interval, if we have an interval, the derivative of the integral from a to x, all you have to do is plug in the x, because what happens with a derivative and an integral? They will cancel each other. So we just have to plug in x into the function, and that is it. So here's an example of that. We have from 0 to x the integral of square root of t squared plus 1 dt, but we're taking the derivative of that, so they cancel. The only thing we need to do is put the x in for t. That was using our second theorem. And we don't actually do anything more than that. And that was section 4 on the fundamental theorem of calculus.